Hey Mark, want to set for heat transfer in the library?
Dude, it's full. There's no room.
I have the solution for that. With the porta table.
Kinematic analysis. The kinematic analysis for the portable table requires that the table legs make a 90-degree angle when fully deployed and the coupler link to have a 45-degree angle to give the table legs enough support to be sufficiently rigid to resist collapsing into its folding position. Using analytical synthesis in Excel, we were able to find the exact length of the coupler link and the angle velocity of the table leg, as well as where the slider will come to a stop. We assume that the slider will be moving at a constant speed of 1 inch per second. It will stop at 4 inches from the inner surface of the table skirt, having 0.667 radians per second angle velocity and the coupler link length of 5.6569. Examining the initial position, we were able to calculate the transmission angle and the starting position of the slider, which it all depends on what offset we use to torque the legs into its position. We decided to use a 2.5-inch offset, having a transmission angle of 26.23 degrees and 6.57 inches from the center of the table.
The goal for this analysis was to find the import torque needed to deploy the mechanism's legs. We needed this torque to overcome the weight of the tabletop as well as the weight of the sliders. Some of the assumptions we made for this analysis was that there was no friction between the joints. To calculate the moment of inertia, links are assumed to be thin rods spinning on one end. Weight of the table is evenly distributed among the 4 legs, and we chose to ignore the weight of the mechanism links since their weight is so small compared to the rest of the assembly. First, parts were separated and a free body diagram of each part was made. From the free body diagram, we were able to get the equations of motion for the assembly. The 9 resulting equations we put into matrix form and solved for variables. The resulting torque needed came out to be 49.38 pounds per inch.
Stress analysis. The main purpose of the stress analysis was to analyze the table legs for failure due to buckling. Because the legs were supporting the weight of the table and the additional load, plus their rather long and slender design, these were most likely to fail. First, some assumptions needed to be made. The first assumption was that the legs were made of a constant material. In our case, we used white oak. The legs would also have a constant cross-sectional area throughout and would evenly distribute the load between the 4 legs. After our assumptions were made, we had to first calculate the moment of inertia for our legs with the assumed dimension. Once the moment of inertia was calculated, using the properties of white oak, we needed to calculate the slenderness ratio. Once our slenderness ratio was calculated, we had to compare it to the slenderness ratio at point D in order to tell if the leg would be considered an intermediate or long column. Our legs were found to be intermediate, so we had to use Johnson's equation to calculate the critical stress. We calculated the critical stress to be 2900 psi and our actual stress to be 8.125 psi using a load of 65 pounds. These values gave us a factor of safety of 356. This table shows the various moments of inertia for the different cross-sectional areas. This table shows the various factor of safeties for the decreasing cross-sectional areas of the leg.